Hello, everyone. Welcome to today's live broadcast, Improving Larger Protein Separations Using 1,000 Angstrom Superficially Porous Particles. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this educational web seminar presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, just what does smarter chromatography mean? It means that when MacMod makes a recommendation to you about an HPLC or UHPLC product, it is to partner with you to offer innovative solutions to your complex problems. They use advanced, state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their 25-plus years of experience in the LC column business, their technical expertise, and their manufacturing network to help you solve your toughest application problems. They provide up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. That is what smarter chromatography means. For more information, please visit them on the web at mac-mod.com. We have a few housekeeping announcements before we get started. The webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of your slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speaker. We're very pleased to be joined today by Dr. Barry Boyes. Dr. Barry Boyes is the Vice President of R&D at Advanced Materials Technologies, or AMT, located in Wilmington, Delaware. Barry completed a BSc in Biochemistry at the University of Alberta, then a PhD in Neuroscience at the University of British Columbia in Canada, under the supervision of Professor Edith G. McGeer. Barry then worked at DuPont Central Research and later Rocklin Technologies, developing a variety of products and technologies for biomolecule separations. HP acquired Rocklin in 1997, which later became Agilent Technologies. At HP and Agilent, Barry served in a variety of roles. In 2006, he became the VP of R&D at the Edgewood, Maryland site of Smiths Detection, developing and commercializing field-ready biothreat detectors. In 2009, Barry returned to developing separations technologies at AMT, using the new superficially porous particles pioneered by Jack Kirkland. Barry Boyes has published widely and is an adjunct professor of chemistry at the University of Georgia, continuing collaborations on protein modification analysis, CNS disease investigations, and contributing to teaching proteomics and separation science. Barry, thank you for joining us today. You have the floor.
Thank you very much, Laura, and thank you for that kind introduction. Hopefully the line we have is good and there's no problem hearing me. So as introduced by Laura, my name is Barry Boyes, and I'll be talking about the use of large pore size superficially porous particles for protein separations, and hopefully I'll convince you that you can carry out separations of particularly large proteins using a new 1,000 angstrom superficially porous particulate material. As mentioned, I work at Advanced Materials Technologies. We have been working on the enablement of superficially porous particles for past a decade now, and that'll be reflected in today's discussion. On the agenda, I will discuss superficially porous particles. Our particular trade name for these is the fused core particles. We observe that these are highly efficient materials for conducting both small molecule and large molecule separations. Today's discussion will really focus around separations in reverse phase for peptides and proteins. And as is typical, these separations are conducted under acidic conditions, with a gradient of a suitable organic modifier, typically acetonitrile, but in some of the examples that I'll show you, we also use alcohol mixes. A lot of today's discussion will be concerned with pore size, and I will try to convince you that pore size needs to be appropriately matched to your samples of interest. Now, in particular, we're going to spend time discussing large pore or macroporous, superficially porous particles, a 400 angstrom pore size material that has been commercially available for a couple of years now, and a most recently introduced 1,000 angstrom pore size that we find useful for intact protein separations. Throughout the presentation, you'll see application examples. I'll try to spend a little bit of time on this in case they are similar to things that you might currently need to do in terms of separations in your laboratory. If one looks at chromatographic separations, and there's really always two central drivers in terms of needs that can always be improved. The first is speed. Everybody wants to do more samples faster, and of course they want the highest resolution that they can maintain in order to get a good quality separation. Now, if you're going to do faster or higher resolution separations, you have a relatively narrow range of conditions that or of materials that you can select for stationary phases. These can include, of course, smaller particle-packed beds. In general, as particle size decreases, efficiency increases. There's also a class of materials referred to as monoliths, which are produced essentially as a unitary separations device. And of course, there's open tubular columns, where essentially there is a stationary phase that's also the containing vessel. And this has become increasingly popular, for example, in not only capillary separations with small tubular columns, but also so-called chip formats, where the channels can be spherical or other geometric arrangements. Now, with respect to smaller particle-packed beds, we have three choices. We have totally or fully porous particles, and in my talk you may see this as an FPP, that stands for fully porous particle. These can flow through the particle as well as undertake rather tortuous paths of diffusion through the particle itself. There's not porous particles, also in older literature referred to as pellicular particles, and these are solid bodies which are generally spherical in shape. Or there's really what concerns us the most today, partly porous or superficially porous particles. And this is a technology that we have worked very hard on, stretching back over actually almost 30 years now. That'll be really the focus of today's discussion. On this slide, we see a cartoon version on the left side of how a superficially porous particle is intended to look, with a solid core at the center of the particle. That's a solid silica sphere, and surrounding it a superficially porous shell, also made of silica, assembled from nanoparticulate silica sols. In the first instance, and it's pushing 10 years ago now, we brought to market a material which is shown on that cartoon being a 2.7 micron particle diameter with a half micron porous shell and a 1.7 micron solid core. And you can see that what we actually wanted to build is something we did build, as shown by the sectioned transmission electron micrograph on the right side, where you can see the solid core in the center of the particle and a porous shell surrounding that solid core. Now, the logic behind the particle is that by having an impermeable solid core in the center of the particle, you reduce the diffusion path through which an analyte molecule needs to diffuse to enter and exit the porous structure of the chromatographic column packing material. So the geometry is in your favor. You have a shorter diffusion path. Diffusion limitations are one of the major degrading contributors for column efficiency. Because you have a short diffusion path, you can generate very high efficiency separations whilst not requiring the use of very small diameter packed particle beds. So this means that you have a comparably lower back pressure due to the particle design. This relieves you of some of the requirements of going to very high pressure in order to get very efficient separations. So it reduces the degree of specialization need for the chromatographic instrument. And because these are larger particles, we don't need to use very small filters to keep them in the packed bed column. And that means that we have somewhat better tolerance to particulate impurities in the flowing mobile phase. But the overriding purpose for this design of particulate materials is that we can maintain high resolution at high linear velocities, high flow rates, because we do have a flat C term in the so-called Van Diemter relationship. In other words, as you accelerate the separation, you do not lose as much column efficiency as is typical with a fully porous particle. Now this is data that's actually 10 years old this year, shown on the slide where we showed initial proof of principle in 2007 comparing superficially porous particles. That's the bottom of the curves on this Van Diemter plot. That's a plot of column efficiency on the vertical axis versus linear velocity or mobile phase velocity on the horizontal axis. And increased column efficiency, increased ability to carry out fast separations is best low on the vertical axis rather than high. As you increase speed of the separation with increasing horizontal axis distance, you want the slope of that increase, loss of efficiency, to be minimized. This is the so-called Van Diemter term. And as you can see, comparing these totally porous or fully porous particles to a superficially porous particle, even though we have a little bit larger particle size, we have much better efficiency with a superficially porous particle. Now, we started a number of years ago to extend this concept to separation of biomolecules. And the first class of biomolecules we were interested in was peptides. When we looked at the so-called standard 90 angstrom pore size halo materials shown on the top chromatograms in this diagram, for small peptides, that material was quite appropriate. The peak widths are good, separation capability. When we began to look at larger polypeptides like insulin, ribonuclease, small protein, we see that 160 angstrom or above is required for pore size in order to get good quality separations, that is, minimization of the peak widths for those specific molecules, and maintenance of high quality separations. And you can see that by comparing the peak widths of the later eluting peaks, ribonuclease and insulin, cytochrome C and lysozyme, comparing a 90 angstrom pore size material to 160 angstrom pore size material. Again, using typical acidic mobile phase conditions. Also, somewhat elevated temperature conditions. And we'll talk a little bit more about why temperature is quite important. So in this plot, again, a similar linear velocity versus efficiency plot. we can see even at 4,000 molecular weight, which is the approximate molecular weight for the beta amyloid 1 to 38 peptide, a 90 angstrom pore size material performs comparatively poorly compared to a 160 angstrom pore size material. Whereas leucine and kephalin, shown on the bottom curve, performs about the same, whether it's 160 or 90 angstrom. In other words, this is a molecular weight or molecular volume dependent characteristic that depends upon the pore size being sufficiently large to allow good column efficiency. The red line that's labeled 179% lower is the decrease in plate height when one goes from a 90 angstrom to 160 angstrom pore size material at a pretty aggressive flow rate. In this case, that would have been about a 2.5 or 3 milliliter per minute flow rate on a 4.6 millimeter ID column. Now, I mentioned operation at elevated temperature is important. Design of chromatographic material to tolerate it is important. When I say elevated temperature, I generally am referring to above 60 degrees centigrade, again, under typical low pH conditions. This slide shows an example of the separation of the amyloid peptides derived from the so-called C-terminus of the amyloid precursor polypeptide. And in this case, by comparing the peak heights or peak areas for some of the less well-behaved amyloid peptides and their fragments, you can see that to get full recovery, you need to not just operate at 60 degrees centigrade, but in the case of, for example, the A beta 17 to 42 sequence, you need to get up above 90 degrees centigrade. And this is important for two reasons. One is we find increasingly that operation at elevated temperature between really above 70 degrees is quite important, not just for somewhat specialized, badly behaved peptides like the amyloids are, but also this is the case for many protein separations in order to get full recovery, that is full elution and recovery of either your peptide or protein. And this must be considered, the use of these aggressive conditions must be considered in the design of appropriate chromatographic materials. This example shows another, I tend to think of separation speed and separation efficiency as two sides of the same coin. You can do very fast separations, and at sufficiently high speed, you will begin to lose resolution, or you can do very high resolution separations. But getting the two to work together requires a change in technology, Jim. And I would argue that's what superficially porous particles allow. So in this case, we're showing separation of a complex sample, a tryptic digest of apotransferrin. And the three different panels show an increasing speed of separation, that is higher linear velocity separation. So faster with the same gradient slope. In this case, with a 2.1 millimeter ID column at rather high speed, 0.75 mils per minute on the top panel, at 1 mil per minute in the middle, and at 1.5 mils per minute on the bottom panel. So pretty fast going to very fast. And if you compare the resolution and peak capacity or ability to resolve this complex mixture across these aggressive flow rate conditions, faster separation time, you can see that there's relatively limited degradation of the resolution capability. So I put this up to remind people that when you're using superficially porous materials, superficially porous particulate materials, one of the reasons for their design is to please go ahead and try a faster separation. In many cases, you'll be pleasantly surprised that you lose very little in terms of resolution. So wide pore, superficially porous particles were originally conceived, and again, this goes back pushing 25 years now, for the needs of bioanalytical science. And even though we found that superficially porous particles are quite useful for fast separations, for high efficiency separations of smaller molecules, where we really believe they shine is in the separation of larger molecules, and in particular those of bioanalytical interest in protein science. So in order to really enable this technology, what do you need to do? Well, you've got to have the right pore size, and I'll show you a number of examples of how that is an inherently true statement. It makes sense because restricted diffusion, that is the diffusional processes that take your analyte molecule into and out of the porous shell of these particles. If you restrict that diffusion process in any way, you're going to limit efficiency, and you're also, somewhat surprisingly, going to limit load capacity. So peak capacity effects, that is the ability to resolve a complex center, are also dependent on how exactly you enlarge those pores. So there's both kinetic components to that, that is mass transfer characteristics, as well as if you don't have any porous material there, then you may have retention limitations. In other words, getting a sufficient peak capacity because of a large enough gradient separation range. Now, all of this involves essentially modeling out particle geometry and optimizing the surface area to volume relationship while maintaining a sufficient shell thickness, but not too thick so that you can block the diffusion path. So you have to have the right sizes of the pores with a correct particle size distribution, pore size distribution, and thickness. And of course, you've got to get the chemistry right. So we spent quite a lot of time really exploring these relationships in order to drive conclusions about what's the right sizes, what's the right geometries. So early on, when we were looking at separations of even larger proteins, like a monoclonal antibody, as shown in this slide, we saw clearly 160 angstrom pore size material was not sufficient. And you can see that because of the broadened peak width on a 160 angstrom pore size material versus a 400 angstrom pore size material. Even though the particles are just a little bit larger on the 400 angstrom pore size material, the improvement in peak shape, that is width of the peak, is obvious. So we know it has to be above 160 angstrom. And at the time that we were really diving into this, the only other commercially available enlarged pore, superficially porous particle that was available to us commercially, not made by us, was a 200 angstrom pore size superficially porous particle. And when we looked at it and some moderate size proteins, chymotrypsinogen, the beta-galactosidase subunits, etc., we saw that comparing that to a 400 angstrom pore size material showed much better peak shape, much better peak widths. So we knew 200 was likely to be insufficient, and we went up to 400 and in fact, we got sufficiently good results that we felt that the 400 was a good place to be. This is a cartoon on the left-hand side showing the design of the particle with a 3-micron solid core interior, a 0.2 micron thick shell with 400 angstrom pore size. And on the right-hand side, you can see electron micrographic analysis that shows that, in fact, we were able to make what we designed. And you can even see the porous structures are apparent with these 400 angstrom pores in those particles. But what we've done is sectioned the particle using fast ion bombardment, so-called FIB, imaging technique where we can cut the particle open and look at the solid core versus the porous shell. So we looked at a lot of different variations in terms of pore sizes, thicknesses of the shell, solid core, et cetera, and have characterized them with a variety of analytes for analytical purposes, but most specifically, we've looked quite carefully at what works best for proteins. And I can say that the theory and the modeling around this is complex. And predicting what is best for protein can be, I would say, guideposted, but is not available from first principles of biophysics. So really this means that you need to look at the compromises in diffusion path, as well as very carefully look at the effects of efficiency for actual protein separation. Now, as an example that this 400 angstrom pore size material is good and appropriate for protein separations and represents a meaningful improvement in the technology, this is a comparison of that kind of material to a sub 2 micron 300 angstrom fully porous particle, both with C4 type bonded phases. And as you can see, the numbers over top the peaks, the resolved proteins represent the peak widths. So in fact, the peak widths are better, the column efficiency is improved. And we described this a couple of years back, certainly can be the case, when we look at the comparison of the effect of improving the pore size and the use of superficially porous particles versus very small diameter fully porous. We have continued in this vein, and I can introduce the new 1,000 angstrom pore size particles for protein separations. Again, with the cartoon on the left, this is a 1.7 micron solid core material with a half micron thick shell with a 1,000 angstrom pore size fully superficially porous shell. And you can see on the right hand the electron micrographs that show that in fact the particles do remain spherical, and that the in this case the pore size is even more obvious in the FIB section particle with the solid core in the center and a spherical shell with 1,000 angstrom pores present. Now, I'm going to describe a little bit here about some of the properties of this family of materials that we've brought to market. But first, to the bottom right-hand side, you'll see a table that describes the approximate size of different classes of compounds, small drugs through large proteins. And at the top of the panel, you'll see a description of the pore sizes, the center of those pore size distributions, with pore width on the bottom of axis of that graph, and on the verticals, two different scales of what's essentially the pore volume available to molecules. Now, the idea is that we want to have materials that have sufficiently large pores across their distribution to include at least 90% of the available pore volume available to the molecules of interest. So this is how we came up with these particular sizes of pores as being the sensible place to be. Now, why do we have two vertical axes? Well, I described the 400 angstrom pore size material as having a 0.2 micron shell. And we did that specifically to allow very fast mass transfer, a very thin shell on that particle. The 1,000 angstrom pore size, with its larger pores, needed to have a somewhat thicker shell, and that also reinstated some of the pore volume available in that morphology. So that's why there's a slight difference there. Now, This becomes important when we begin to take a look at not only what I've really focused on, which is, well, what about the peak width or the peak capacity, but also what's the net retention when we look at separation, because that will have an effect on peak capacity. So this is a family of materials that is designed specifically with different classes of materials for each of the pore size ranges. Small molecules, best handled with 90 angstrom pore size material, 160 angstrom for peptides and like-sized molecules, and for smaller intermediate-sized proteins, 400 angstrom performs admirably, and for the 1,000 angstrom material, we're really talking about intact proteins and very large protein complexes that are stable under the separation conditions. So I just want to give you a flavor for how we came about those decisions in terms of chromatographic thinking. Here we see a comparison of a fully porous particle, sub 2 micron, 300 angstrom pore size material, separating a simple protein mixture from relatively small at the front with ribonuclease, and then the third peak out being enolase at about 93 kilodaltons and carbonic anhydrase at about 30. If we look across these different materials, we can see the 160 angstrom material works just fine for smaller things like ribonuclease, a little bit less efficiency compared to a 300 angstrom pore size material or above, that is the 400 or 1,000, whether it's fully porous or not. When we get up to the larger proteins, like enolase or carbonic anhydrase, the last two peaks out, we can see that a 300 angstrom pore size material is insufficient, and that a superficially porous particle morphology also helps. So in this case, the 400 versus the 1,000 show very subtle differences at that molecular weight range. But the fully porous particle combined with the enlarged pores clearly give you an advantage in terms of generating better peak widths. You'll note I also include in the bottom here a bullet point that says similar results in TFA, DFA, and formic acid as mobile phase acidic modifiers. And the reason why I mention that is we use a number of different mobile phase modifiers. I'll describe that after I introduce the idea of why we actually want to separate much larger molecular weight materials. And that's shown on this slide, really. And it's certainly fair to say that in the last 5 or 10 years, that there has been an enormous realignment around the idea of using biotherapeutic proteins, and the most obvious one is, of course, monoclonal antibodies. And I show this to point out really two things. One is that's the front of a publication taken from 2011. And at that point, there were 40 monoclonal antibodies which had either transited or were in the process of transiting FDA approval. This number now is over 400. So it's clear that there is significant medical, therapeutic, and technical interest in monoclonal antibodies, not just because they're crucially important proteins in your immune system, but also because they have become a fundamental biotherapeutic platform. Now, these are large molecules, about 150,000 molecular weight. When you reduce an alkylate, you do break off, so to speak, or release heavy chain and light chain subunits. And the first thing that we looked at, pretty obvious, is a reduced IgG, in this case an IgG2 subtype, where we're looking at the heavy chain and light chain. So in this case, on a 400 angstrom protein material with typical trifluoroacetic acid conditions, heavy chain, light chain separation very straightforward, and the variance of heavy chains very straightforward to be resolved chromatographically. And you'll note under pretty reasonable analytical time scale. So a good separation for that type of sample. As we started looking more closely at what conditions were tolerable in terms of work that we were doing in the lab, and many people do in the lab, we use a combination of not just UV detector, but also mass spectral detector and other detectors. But mass spec is particularly important for us because as we get to increasingly complex and high molecular weight samples, we just have to have mass spec in order to sort out what it is that we're doing in terms of protein structure and function and variance. So we've spent quite a bit of time looking at different mobile phase modifiers for conducting protein LC coupled with high-resolution mass spectrometry. And in the following examples, you'll see us mentioning either formic acid, that's the first compound shown here, or trifluoroacetic acid, very standard mobile phase acidic modifier, and as well right next to it, difluoroacetic acid, which is the same compound, but with one less fluorine on the methyl group. We've found, in particular, by looking at these different materials, that in the top, in this slide, on the top is UV traces. On the bottom is total ion current, so the mass spectrometer signal. We found that, as everybody else has observed, formic acid is the best pick in terms of use in mass spectrometry for ionization, for giving a useful signal. And trifluoroacetic has a very strong tendency to ion pair with basic side chains on peptides and to inhibit the mass spectral signal. Difluoroacetic acid shows considerably less problems in use in mass spectrometry. For peptides, this shows up as a much better signal, a much less ionization suppression than you see with trifluoroacetic acid. We use DFA quite a lot, almost exclusively these days, for tryptic digest and other peptide separations analysis, where we couple LC mass spectrometry. For proteins, it's a slightly different story, and really this is a molecular weight dependent function. But again, we see a similar pattern. Formic acid works great for mass spectrometry, not as good for many proteins as trifluoroacetic acid. We can see this by comparing the UV signal on the left-hand side of this panel versus the mass spectral signal on the right hand. But you can see also TFA really kills your signal for proteins. These two detectors were coupled in series. Difluoroacetic acid, again, quite high quality separation in terms of peak widths for each of these proteins. On the right-hand side, you can see that there is clearly some ionization suppression. The bottom panel shows a slightly different fluorinated acid. So the net effect is exactly the same as what we saw for peptides, which is formic acid works absolutely the best for ionization, trifluoroacetic acid the worst. The best for chromatography is trifluoroacetic acid, and formic acid is actually the worst in terms of peak shape and peak width. Difluoroacetic acid sits in between. The ionization suppression is greater with difluoroacetic acid than you get with smaller peptides. But we find it useful because unlike TFA, it's easy to get rid of DFA from your instrumentation. So do we get some ionization suppression with it? Absolutely, especially when you get up to IgGs, intact IgGs. For fragments of IgGs, works just great, and we do a lot of LCMS analysis there. In this case, we're showing an IDE-S digest of intact IgG, a monoclonal antibody. This one is also, I believe, trastuzumab. And we typically do this kind of digest with and without DTT so that we can resolve actually we can resolve all of the different fragments that you could generate this way. We run them in pairs so that we get the FAB2 or FAB prime 2, the FD fragment, the light chains and their variants when they're resolved, as well as the FC chains that can be resolved. And by doing this with online mass spectrometry, high resolution, we can chromatographically and mass spectrally resolve the variants of the polypeptide chain as well as the glycosylation variant. You can see that on the left-hand side when we deconvolute the mass spectral data for the FC released fragment. That's with a 400 angstrom pore size material, again using DFA in the mobile phase. Now, when you get up to intact IgGs, so typical monoclonal antibodies, this is why we need to use something other than formic acid. And this is very typical for an intact IgG, which is the formic acid. If you use formic acid in a mobile phase, you get rather a broad misshapen and undesirable chromatographic result. By comparison, trifluoroacetic acid is shown on the bottom, much better peak shape clearly, and difluoroacetic acid is very similar to trifluoroacetic acid in terms of the peak shape you can obtain. In this case, this was using the Sigma standard, and this is an intact monoclonal antibody. When we use mass spectrometry in series with this separation, we do it using difluoroacetic acid in the mobile phase. We can resolve the major species present by deconvoluting the high-resolution mass spectra. We use the Orbitrap typically doing that. Now, back to the subject of pore size. In this case, we see a separation of trastuzumab, so a therapeutic monoclonal antibody, resolved, and its impurities or variants, should I say, resolved using a sub-2 micron, 300 angstrom fully porous particle, C4 bonded phase material, compared to a 400 angstrom 3.4 micron halo protein column, and the new 2.7 micron 1000 angstrom pore size superficially porous particle halo protein C4. And you can see just even visually that the peak shapes are much better with the 400 and 1000 angstrom pore size material. The best results are obtained with this new 1000 angstrom pore size superficially porous particle. The variants from the major peak, predominantly trisulfide and other sulfide variants, but clear improvement in terms of separation efficiency. This is not unique to that monoclonal antibody. When we look at the average peak width, in this case looking at multiple columns injected multiple times to get averages, to generate some statistics on this, so to speak, and looking at 6 different monoclonal antibodies, what we see is about a 3-fold improvement relative to a sub-2 micron fully porous particle in terms of peak shape. Clearly an improvement in terms of column efficiency and ability to chromatographically resolve intact IgGs. This is not a unique feature based on picking a particular flow rate. In this case, this is on the vertical axis, a measure of column efficiency, in this case peak volume, that is the peak width, multiplied by the flow rate, and on the horizontal axis, the flow rate under which the separation was conducted. Now in order to fairly compare across these conditions, we used a fixed volume gradient of 4.8 milliliters, varied the flow rate, and looked at the effective flow rate on column efficiency. And what we see comparing a fully porous to a superficially porous particle is that at every flow rate, up to really the pressure limit for the instrument, a superficially porous particle just does better. Whether it's 400 angstrom pore size or 1,000 angstrom pore size, having a superficially porous particle gives you a specific and readily apparent kinetic advantage, and that this increases with the linear velocity. So that would make sense in terms of it being a mass transfer limitation with even small fully porous particles. So at any given flow rate, a superficially porous particle works better, and where it works best is with the, in this case, for an intact IgG, the 1,000 angstrom pore size material. What about load? Well, if we have a superficially porous particle, inside of that is a non-porous solid silica core. And that solid silica core contributes nothing to the ability to load a sample. It's not porous. It has no surface area. Does this limit the utility of superficially porous particles? Well, we looked at peak width as a function of load injected for monoclonal antibodies. And again, this is not unique to this particular monoclonal antibody. We see it with all of the monoclonal antibodies we've looked at. At any load level, the 1,000 angstrom pore size material outperforms, in terms of peak width, the smaller pore, higher surface area, small diameter, particle diameter, fully porous particle. So even though we have significantly less surface area, the surface area that's there is productive surface area, in that it's able to be reached by the monoclonal antibody structure. And what I mean by that is, by the term productive surface area, is that it doesn't really matter how much surface is in your particle if the molecule that you're trying to get to that surface can't get to that surface area. So load is a function not just of surface area, but productive surface area, and we have maximized that by using the larger pore, superficially porous material. So we do a number of different, we've looked at a number of different applications of this, pretty straightforward stuff. In this case, looking at the analysis of IgG, in this case IgG1, trastuzumab in the glycosylated or PNGase F deglycosylated state, and collecting mass spectral data so that we can deconvolute the high-resolution mass spectral data and look at glycosylation variants. And the way we do that, and it's shown in the next slide, this is the raw mass spectral data across those chromatographic peaks, comparing the glycosylated and deglycosylated IgG. And you can see in the top set of panels, whether with blown up or deconvoluted data, that you've released the glycans. You can calculate by comparing these two what the level of occupancy was for that chromatographically resolved material in terms of its oligosaccharide composition. With G0, G0F. The reason why there's two of each is, of course, it's on the right side versus the left side of that Y-shaped IgG molecule. So the moral of the story here is, yes, we can get a high-resolution mass spectral data at high speed with high resolution using this chromatographic approach with online mass spectrometry. We've looked a little bit at more complex monoclonal antibodies, in this case looking at IgG2 subclass, as well more recently at IgGAs and IgGMs. I won't have time to go into that today, but we'll show more data on that this summer. In the case of IgG2s, the interest here is that we don't simply have, like we do with an IgG1, a major disulfide bridged form. We have spontaneous formation of multiple types of disulfide bonded intact IgG forms. So different combinations of how the heavy chain and the light chains are cross-linked through disulfides. We also, not shown in this diagram, have trisulfide and other variants of IgG2. So IgG2 is actually a fairly complex structure compared to the prototypic IgG1. And in this case, we're showing separation of a therapeutic monoclonal antibody, Prolia, which is an IgG2, resolved on the haloprotein 1000 angstrom, so this new material, and compared to a sub-2 micron 300 angstrom fully porous particle separation in the same conditions. And as you can see, there is a lot more complexity that's being resolved with the superficially porous 1000 angstrom pore size material. We have not characterized all of these variants. There's clearly a lot of variants of the IgG2 present. We're having to go in and collect all of the variants that we can access and triptychally digest and analyze all of those. What I can tell you is that across that peak, looking at the Orbitrap data, that these are all, in fact, pretty near or very close to being proven as isobaric structures. There's glycosylation variants, but the primary structure itself is within 10 mass units, isobaric structures. So these are not variants at the polypeptide or the glycosylation level. These are, in fact, variants at the disulfide bridging. When we look at the 400 versus the 1000 angstrom pore size material, we get a slightly different pattern. We think the 1000, when you get up to a sample this large and complex, large in terms of molecular weight and complex in terms of the number of disulfide variants, it makes sense to us that we are resolving, in fact, more materials on the 1000 angstrom pore size, and that is the material and separation that we're using to further characterize that rather complex mixture of IgG2 variants. So let me conclude. Hopefully I've convinced you that fused core silica packing materials are useful for larger molecule separations, that you don't need to go to very short columns or very high pressure operation. In other words, you can maximize the ability to resolve complex mixtures. The enlarged pore size superficially porous particles of 400 angstrom and 1000 angstrom are particularly useful for protein structure function analysis. And they are sufficiently robust that we can take them up to high flow rates or high back pressures if you really want to, in order to speed your separation or in order to put multiple columns or longer columns in series to maximize your resolution. There's been a lot of focus in this discussion today on IgGs. These are large and complex molecules, and you need all the help you can get for high-performance separations and characterization of, in some cases, in the case of IgG2, these rather complex mixtures of variants. That's best achieved by making sure that you have sufficient pore size and appropriate particle morphology. And with that, I'd like to thank you for your attention and acknowledge some people who have been particularly important to this work at AMT and some of our outside collaborators at the University of Georgia. I'd also like to mention two people I forgot to put on the list here from Advanced Materials. That is Dr. Kirkland and as well Brian Wagner. And I'd also like to thank AMT as well as the NIH for their support of this work. And I will stop there and hand it back to you, Laura.
Great. Thank you so much, Barry. Before we move to audience questions, we have two quick polling questions that we would like all of you in the audience to participate in. You can click directly on your screen to submit your answers. So on your screen now, you can see the first question. Which manufacturer do you currently source your protein columns from? Waters, Agilent, Phenomenex, Toso Bioscience, Sapelco, Thermo Fisher Scientific, or MacMod Analytical? So once again, click directly on your screen to answer. Which manufacturer do you currently source your protein columns from? Give you one more moment there. Okay, and here's our second question. Again, click directly on the screen to answer. Would you be interested in a personal consultation on your method development for your protein analysis? Yes or no? So once again, would you be interested in a personal consultation on your method development for your protein analysis? Yes or no? All right, we just have a couple minutes, but I think we can get a couple questions from the audience in. So here's the first one. Barry, at 100 degrees C, what protects the protein from being denatured?
Under reverse phase conditions, I would say that you don't protect the protein from being denatured. In fact, by and large, reverse phase is, with few exceptions, an inherently denaturing technique. Now, what that means is that if you don't have disulfide bridged subunits, you're quite likely to actually be separating subunits rather than intact proteins. But certainly, in anything under acidic conditions with an organic modifier, as is typically present in reverse phase, you have conditions that are quite denaturing for native protein structure.
Thank you. What is the longevity in terms of number of injections of your superficially porous particle columns? And is there a correlation with the shell thickness, between the shell thickness and the lifetime of the column?
Right. Okay. Well, part of the challenge for us has been to build a superficially porous particle which is as robust or more robust than any commercially available product. So we feel that we've done that job well, and you should see column lifetimes as good or better than any fully porous particle material that's available to you. The solid core actually helps to stabilize the structure, and you should not see particular problems with respect to physical or chemical instability of any properly made superficially porous particle.
Have you tried the 1,000 angstrom column for the separation of protein aggregates?
Yes, but it does not, how could I put this? Proving that they're aggregates under the conditions that you conduct reverse phase separations is problematic. So it's not, unless you're talking about covalently aggregated or covalently stabilized aggregates, it would not be the technical approach to resolve based on aggregation state. You can resolve aggregated from non-aggregated proteins by reverse phase, but typically not under conditions that are high resolution reverse phase conditions.
Fantastic. Let's take one last very quick question, very briefly. Wouldn't the smaller particle size on the 1,000 angstrom particle also elicit better resolution and efficiencies of proteins and antibodies, regardless of pore size?
Nope. You need big enough pores in order to get good quality separation. So, for example, if we, and I showed in earlier slides an example of 160 angstrom pore size material, which was 2.7 micron, compared to a 400 angstrom 3.4 micron material. So the 2.7 angstrom, 160 angstrom, the 2.7 micron 160 angstrom material is not something that we actually make commercially. We used it specifically as a prototype to look at the effects of pore size and particle size. And with IgG, for example, with a monoclonal antibody, the performance there with 160 angstroms is really inferior to what you see with 1,000 angstrom or even a 400 angstrom pore size material.
Fantastic. Well, Barry, thank you.
Slide. Yeah.
I'm sorry.
Yep.
You can pull up the slide briefly as I'm wrapping up if you want to push it out to the audience.
There you go. This is an example of that.
Excellent. Thank you. We'll leave it up there for a moment. Okay. Well, we need to wrap up. Barry, thank you so much for your talk today and for answering those questions.
And thank you for your attention today. And I'll leave it over to you, Laura.
Thank you. I'd also like to thank our sponsor, MacMod, for making today's webcast possible. Today's program will be available for on-demand viewing through April of next year. You'll receive an email from LCGC alerting you when the webcast is available for replay. We invite you to forward that announcement to any colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.